A dot isn't the best way to try to sum up how electrons come and go. They are the states of a matter field that follows an equation that Dirac wrote. The Schrodinger part of the whole equation will just lead in sub C when it expands. Now get that.
In this video, we're going to cover the Hill equation, and Hill plots. For both myoglobin and hemoglobin. So we've started covering this a little bit in class, or we covered it a little bit ago, and so now we're just going to flesh it out a little bit. I'm going to give you guys a little bit more detail about it. You will not have to derive the Hill equation, but you should know how we can get the Hill plots from the Hill equation, what they tell us, and how we can make them linear. You'll not have to calculate anything from them. So let's go ahead and get started with myoglobin first. So we know myoglobin binds to one oxygen. It can dissociate at some constant, Kd, leading us to myoglobin plus oxygen gas. And so Kd, so if we look at the equation for the dissociation constant, it'll be the products over the reactants. And so we talked a little bit about this concept of Y in class as fractional saturation, where if Y equals 0, it's unsaturated. If Y equals 1, it's fully saturated. And if Y equals 0.5, it's 50-50. Half of it's saturated, half of it isn't. But we can define Y then as this. And so the reason why we can do this is because if everything is fully saturated, it will be up here, and nothing will be down here, and so that will equal 1. If it's unsaturated, everything is down at the bottom, nothing is at top, that's 0. And then again, if half of it's on top, half of it's on bottom, it'll be 50-50 ratio. And so what we can do is we can rearrange this equation for the Kd to get this. MbO2 is equal to MbO2 divided by Kd. So if in algebra or in any other equation, if you have a denominator that you want to move out here, all you have to do is switch what's out there with your denominator, and that's why we get the equation MbO2 is equal to the concentration of myoglobin times the concentration of oxygen divided by Kd. And so then what we're going to do is we're going to combine these two equations. And so what we get is fractional saturation is equal to concentration of myoglobin times the concentration of oxygen divided by Kd let's go back up to this Y equation because I messed up the denominator. I knew something looked funny. And so what you have is you have the bound myoglobin, and what you get is myoglobin plus the myoglobin bound to the oxygen. So then if everything is bound, so if everything is in this state, you get 1. And then if everything is in this state, you would get 0. And then again, if it's 50-50, you would get 1/2. And so let's go ahead and use the real fractional saturation equation for this. And so then what we get is we get myoglobin plus myoglobin times the concentration of oxygen over KD again. And so all we're doing is let me change color so we can see it, is we're taking this equation and plugging it in wherever we see the concentration of the bound myoglobin. So what we can do now is we're just going to multiply everything by KD. And so for the sake of how everything looks, I'm going to switch to a new slide. And so if we multiply everything by KD, we cancel out all of these denominators. And what we get is Y is equal to myoglobin, oxygen, divided by myoglobin times KD, plus, again, myoglobin, oxygen. And so what we can do is we can find terms or things that are the same. So we know, or we can see that this myoglobin and this myoglobin are the same. And so what we're going to do is we're going to pull these two things out, and what we're going to get what we're going to be left with is this. Y is equal to myoglobin times oxygen divided by myoglobin times KD plus O2. And so now what we see is we have a concentration of myoglobin on top and a concentration of myoglobin on bottom that is separate. So we can reduce, or we can cross off both of those. And since we're dealing with a gas, the concentration of O2 is equivalent to the partial pressure of O2. And so what we're going to do is we're going to substitute those back in. We're going to substitute pressure of O2 for concentration. And what we get is this. Now in class, I told you guys, when we are at Y is equal to 0.5, that is the same of drawing this equation as this. P 50 divided by KD, or wait, let me back up. Nope, we're not going there. That at Y, when Y is equal to 0.5, we know that KD is equal to something known as P50, which is the pressure with which 50% of the myoglobin is bound. And so from there, what we can do is we can make our final equation. I'll do it in a different color. We'll do it right here, where Y is equal to PO2 divided by P50 plus PO2. And so we said that's the Hill equation that leads to this kind of graph. And so I'm going to quickly draw the graph. I won't draw it in as much detail as I showed you guys in class, to where myoglobin looks like this and oxygen looks like this. And then we can look at the transfer of oxygen to a variety of different places, and I gave you guys why myoglobin is a terrible O2 delivery molecule in the blood. But what I want to look at real quick is that, if Y is equal to fraction saturated, then 1 minus Y is equal to fraction unsaturated. Right, so it's the complete opposite. We're going to take the inverse of percent saturation to get percent unsaturated, or fractional unsaturation. And so the way that we can make the Hill graph linear is by taking Y divided by 1 minus Y. And that is going to equal, so we said Y is equal to this. And we're going to divide it by 1 minus the same thing. What I'm not going to show you, what I'm not going to show you is the mathematical steps that we need to take to go from here to here. If you would like to see them, you can come by the office and we can show them to you. But what we can do is through some manipulation, we can end up with this right here. And so then you guys said in class, and it was absolutely correct, that if to make a hyperbolic curve linear, you need to take the log of it. So what we can do is we can have log of y over 1 minus y is equal to log of O2 over KD. And if we have a log of a fraction and we want to separate it, just like we did with the Henderson-Hasselbalch, I'm going to erase this, we can do the log of y over 1 minus y is equal to the log, and instead of concentration of oxygen, I'm going to put the pressure of oxygen. I'm going to do minus the log, and instead of KD, I'm going to do P50, like what we saw before with the previous equation. And this is known as the Hill equation. This right here with the log is the Hill equation. And what it does, like we said before, is it makes a hyperbolic curve linear. For myoglobin, right, the slope was equal to 1, which means it was non-cooperative binding. So things with non-cooperative binding show an n of 1 when you put them in the Hill equation and you make the straight line. And so what we're going to do is, we're going to move on to hemoglobin. If you guys have any questions, then please let me know. I really want to make sure that we are all on the same page with how this is done. And so what we're going to do, this case, the thing that changes with hemoglobin compared to myoglobin is that you can bind to different ends, or a different number of oxygens, which we'll denote with an N. And so what you're given is hemoglobin plus the N of O2. So if we take the KD, and we're going to do the same thing that we did for myoglobin, except the concentration of O2 now will be raised to the nth power, since we can have a variety of number of of oxygens. And what will be down here is that. And so again, I'm not going to do much of the math like what you saw with the myoglobin. You feel free, if you would like to just work through it so that you could better see it. But I'm going to kind of jump down to the final step, like what we saw with the fractional saturation with myoglobin, to where we get this. And again, if you want to see the steps, please feel free to come see me. I would love to work them out with you and for you, and then we can maybe get a better understanding. And so again, we change the concentration of oxygen to here. This is P50, right? So it's very similar to what we saw with myoglobin. The only difference between hemoglobin and myoglobin are these raised to the nth power, because of how many things they can bind. And so what we can do, and what we want to do with this equation right here, is put it into the Hill equation. So again, what does that look like? And so we know y over 1 minus y is going to equal this, PO2 to the nth, divided by P50 plus PO2 to the nth, divided by 1 minus the same thing. Right? And so again, we can do some manipulations, and what we can get is we can get log of y over y minus 1 is equal to log of the partial pressure of oxygen to the nth power divided by P50 to the nth power. And so I'm not going to show you how we get or why we need P50 to the N. Just know with hemoglobin we need the N in front of the next to the P50. And so what we can do is we can separate them again, like what we did before with myoglobin. Except when we separate them, whenever we separate these and we have an exponent on our number, it needs to move in front of the log. And so here we have n log of oxygen minus the n log of the P50. This n is known as the Hill coefficient. So in the myoglobin case, we didn't have those n's. The n was 1. Whenever you see an n of 1, it is non-cooperative binding. When an n is greater than 1, it is cooperative binding. So what kind of graph can we get? So let's look at the graph for hemoglobin. So this is going to be y over 1 minus y. It's going to be the log of that. So it's a log scale. So it'll be base 10. Let's do 0.1, 0.01, and it can go down. And then so that's the y-axis. On the x-axis we have the partial pressure of oxygen. And again, we'll go ahead and do log of that too. And so what we have is 0.1, we have 1, we have 10, and we have 100. And what we see, so instead of a straight line, like what we saw with myoglobin, so I'm going to just draw this line at 1, just to, we'll explain what it is. So remember, with myoglobin, the n was 1, it's going to look like that. It's going to be a straight line where n equals 1. But what we see is with hemoglobin, it actually kind of makes a sigmoidal curve. And so we can kind of do this. Make it like that. And so it's kind of a sigmoidal curve. And so what's interesting about this curve is that we have two what's known as asymptotes. So asymptotes are lines that approach a hyperbola, but they don't actually touch it. And so what we can do though is we can draw these asymptotes, as I did in purple, and they tell us things. And so the slope of this asymptote, or the slopes of the asymptote, are n equals 1. Right? So it looks like it's a non-cooperative binding. However, when we look at the slope of this in the middle, what we can see is it's about 3. And so suggesting that hemoglobin is cooperatively binding to its oxygen, right? It's a lot easier to bind the second and the third than it is the first. And so what we see is if we take this asymptote where it crosses the number 1 and we drop it down, this is the pressure of oxygen for the first bound molecule of O2. And it's about 30 torr. So then what we can do is we can look at this, where this crosses, and we can drop it down to about there. And this is the partial pressure of the last oxygen bound, right? So it needs a lot less partial pressure to bind the last oxygen than it did for the first, right? Which is what the cooperativity is all about. And so this is what the Hill equation and the Hill graph can tell us about these two oxygen binding proteins and whether something is cooperative or not. If you have any questions about this, please come see me and come talk to me and we'll discuss it. You should be familiar with how hemoglobin works and myoglobin works because you will need that for the exam.